Hey guys, so we're going to do rational exponents today. There's two rules that we're going to talk about. One is that you can't have any improper fractions. So if you have an improper fraction, say like x to the 7/4, you're going to want to break that up. So what I always say to do is kind of turn the 7/4 into a mixed number. So kind of think of that as like x to the 1 3/4. So if you know your properties of exponents, when you have two of the same base, you're going to go ahead and add your exponents. So this will be like x to the first power and x to the 3/4 power. So when you do that, if I were to have these same bases, I would add them together. This 1 would really turn into a 4/4, and that 4/4 plus 3/4 brings us back to the 7/4. So our answer would be x times x to the 3/4. If we tried something else, like, I don't know, y to the 8/3. Again, we have an improper fraction there, so we're going to go ahead and change that 8/3 to a mixed number. So that's going to be y and 2 2/3. So if we want to think about that whole number is going to become one of our exponents, so y squared, and then the fraction is going to become our other exponent. If you were to ultimately add 2 plus 2/3, you're going to get your original improper fraction, but we're saying no improper fraction, so you have to break that up. So y squared times y to the 2/3. The other rule that we're going to talk about is no radicals in the denominator. That's not really a new rule. That's something that we're always saying, but something that is new is that radicals can also be rational exponents. So real quick here, something like x on top and y to the 2/3 on bottom. So that y to the 2/3 is really the cube root of y squared. So you can see that it really is a radical. So what we have to do is we have to try to think about multiplying by something. Just like if you had a radical, you're going to multiply by something. We're going to choose the base y. We're choosing a base y because my problem's starting as a base y. So what we have to do is we have to figure out what exponent we're going to use to get to a whole number. So right now I have 2/3, so I'm going to choose another denominator of 3 because I know that since I have two bases that are the same and I'm multiplying them, I know I'm going to have to add my exponents. So I have a 3, so that's why I'm choosing 3. So I have to figure out what's going to be the numerator of my exponent that when I add 2/3 to it, I get a whole number. And we're looking for the smallest whole number possible. So that's going to be 1/3. And that's simply because 2/3 plus 1/3 gives me 3/3, or that whole number. So whatever I do on the bottom, I'm going to have to do on the top. So I'm going to be left with an x, y to the 1/3 on top, and on the bottom, I'll have y to the 3/3. Now we're not going to leave that as y to the 3/3 because that's weird. So x, y to the 1/3 on top, and then y on the bottom. A lot of people think that you can go ahead and subtract these exponents, that 1/3 and that y. Unfortunately, you can't, because if you did, you would end up with y to the 2/3 on the bottom, which ultimately brings you back to the original problem. Then you have to start all over. All right, so these are some examples off the notes that you can find online. I'm going to go ahead and just start with example E. We're not actually going to do all of these. So if we look at example E, these are the same ones online, like I said. 27 p to the 3rd q all to the 1/3 power. So we really have to think about what we did in class when we were doing just regular properties of exponents. We take this 1/3 power and we distribute it. What we have to understand is that this is going to be 27 to the 1/3 power. 27 to the 1/3 power, not 27 times 1/3. And then we'll have p cubed to the 1/3 power, and we'll have q to the 1/3 power. So remember, properties of exponents, we have this power to a power here. We'll go ahead and multiply those. So 27 to the 1/3 is going to stay just for a second. Then we'll have p to the first, don't write the 1, that's weird, and q to the 1/3. Now you always want to check to see if you can simplify anything. This 27 to the 1/3, if you pop that in your calculator, it's going to give you a 3. Right now, we will be popping things in our calculators, but eventually we will be simplifying those radicals by hand. So just so you're aware, 27 to the 1/3 is the same thing as cube root of 27. That's where that 3 is coming from. We know that this is our final answer because there's no improper fractions, there's no fractions in the denominator, and there's no negative exponents. Those are all things that we want to check for. All right, let's go ahead and skip No, we'll do F. F is tricky. So for F, 27 to the 4 thirds minus 16 to the 3 halves squared. So what you can't do here is you can't distribute. And the reason why you can't distribute is because there's this subtraction sign. So we have to go back to simplifying radicals by hand. So we're going to simplify these with no calculator, which means we're going to change them into radicals because we can mentally do that a little bit easier. So 27 to the 4 thirds is going to be the cube root of 27 to the 4th power. And 16 to the 3 halves is going to be the square root of 16 to the 3rd power. And then all of this is still squared. So the cube root of 27 is 3 to the 4th power still, minus the square root of 16 is 4 to the 3rd power still, everything squared. 3 to the 4th is 81, 4 to the 3rd is 64, that's still squared. Notice that I have not distributed that 2 yet because we still have this subtraction. So my last step is going to be to take 81 minus 64, that's going to give me 17, and I have that squared. So I can finally evaluate that to be 289. So you do want to make sure you're showing all those steps. We will ask to see those. Okay, let's look at G. G says x over x to the 4/9. So the problem you're going to notice here, the issue that we have, is that we have that fraction exponent in the denominator, which is really like a radical in the denominator. So before you think about rationalizing, like that first example I showed you how to get rid of that, you actually don't need to do that because on top we have 1x. We actually have more x's on top. If we think about writing this as an exponent of 9 over 9, you can see we have 9/9 on top and 4/9 on bottom. So there's 5 more 9s. You can really just subtract those and we'll get x to the 5/9. So always try to do things like that before you start rationalizing because you can save yourself a little bit of time. So 5/9 as my exponent is going to be totally okay because it's not an improper fraction. So we'll leave it like that. All right, let's try J. So the 6th root of the 4th root of the square root of x squared. So this problem is a little bit intimidating because there's so many radicals with so many different indices, but if we just change it to rational exponents, it becomes super easy. So start on the inside, x squared. The square root of x becomes a 1/2 exponent. Then the 4th root becomes a 1/4 exponent. And then the 6th root becomes a 1/6 exponent. So I know that there's a lot of powers there, but if you think about your properties of exponents, powers of powers, all you do is multiply those. So ultimately we'll end up with x to the 1 over 24. Now the catch is that if we give you a problem in radical form, you have to give us a problem back in radical form. So right now this x to the 1/24 isn't going to cut it. We got to switch that to radical form, so the 24th root of x. Okay, so here's an example. It's not on your notes. It's something that I just made up just to help us practice a little bit with simplifying those fraction exponents that are improper fractions. So before we can do any of that, what I would go ahead and do is I would distribute this 2. So power to a power, remember you're going to multiply. So 3/2 times 2 is going to just give me x to the 3rd. And then I have 4/5 times 2, which is going to give me 8/5. And then I have 7/3 times 2, which is going to give me 14/3. So the x cubed is totally fine, but the 8/5 and the 14/3 are improper fractions, so we have to break those down. So I think the easiest way to do that, again, is to make that into a mixed number, and that'll help us kind of see what we need for our exponents. So 8/5 becomes 1 3/5. So 1 3/5 are going to be our exponents now, and those will have y's. So my x cubed is going to stay. I'll have y to the 1st, don't write that 1, that's weird. Y to the 3/5. And then if we think about that z, 14/3. So 3, 6, 9, 12 means that I have 4, and then there's 2 left over. So then I'll have a z to the 4th and a z to 2/3. So z to the 4th and z to the 2/3. So we really got to make sure that our final answer, the 2/3, the 3/5, that they are not improper fractions. The numerator is less than the denominator.